Hi there folks, my name is Natalie and I am a member of Gauntlet Cohort 2 and I am excited to show you this week's project, which is a refactoring or new featureizing of an old comprehensive large code base to see how well AI does digesting well-established code. So for this week, I picked LAPACK, which is a comprehensive software library that provides subroutines for linear algebra functions. In essence, this was pretty easy and important choice for me because LAPACK is what powers NumPy, SciPy, PyTorch, and MATLAB on the back end. There are lots of very basic subroutines in matrix multiplication, and they are well used in machine learning or in high performance compute environments. So being able to contribute anything to this 30-plus-year-old 1.5 million line plus code base would mean the world to me. Plus, I've used it myself professionally, so I would really like to learn more about the source code. I've never done Fortran before, so the first thing I did to try and understand this code base was to try and parse out the documentation and then use some agentic tools to understand all the components. So here is DeepWiki, and DeepWiki does a great job of summarizing all the core components of LAPACK. But in essence, LAPACK is consisting of two large libraries. There's the linear algebra package, which is LAPACK, which actually contains the core Fortran code for doing matrix multiplication. And then there's BLAS, which are the basic linear algebra subprograms. They have a C interface, which I believe all of the wrapper programs that I told you about call. I didn't really look at the way that external programs call this thing. I've been focusing so much on the core part of it. And there's a comprehensive testing framework with essentially their own custom-made quality checks and flags for how to compile. And then they also have a large CMake build system, which auto-detects the sort of framework that you have, and also has lots of flags that you can pass in based on whether it's a GPU or a CPU, and lots of things like that. So my first goal was to create a local dev environment, and initially my features were erring on the Python side, but I changed my mind halfway through and now I'm programming in pure Fortran. But my dev setup is the same. In essence, I have a Docker container where I can compile the code base, and the Docker container contains all of the dependencies that I need, so CMake, GCC, and Fortran. So I can kind of show you what that looks like. So we have previous Docker containers from before, but if you notice, here I've got a dev Docker container, I've got a prod Docker container, and I've got a base Docker container. So the base Docker container has the base environment of where LAPACK is right now. The dev Docker container is the one that I use to develop my features. So if I want a feature to be compiled immediately and integrated and I want to test it, then I'll go in there. And the prod Docker container I envision using to test the release version of this application. But what I would do to run it is simply run it in interactive mode with this entry point, and what I would do is I would add a volume, which is the workspace. And then as you can see, I've got all of the libraries. Now if I wanted to build directly in the Docker container, I could build with CMake, but I also took the liberty of creating a Docker Compose file that already has a built-in build command for me. So if I can show you that Docker Compose file, it looks something like this, and this already configures everything I need to compile my LAPACK environment. But in essence, every time I test, I have created a set of testing rules with my machine learning model that tell it how to enter the Docker and enter into interactive mode, specifically just compile the files that I need. So for example, if I am making a new implementation, which is what I'm doing now, I will use gfortran to compile the components individually, and then at the end of it, I will usually run this large Docker Compose step. But to show you my feature and what I'm doing, I am in essence implementing AlphaTensor's matrix multiplication algorithm. AlphaTensor, which is an agent that this group used to try and find more efficient matrix multiplication algorithms. And in essence, the algorithm discovery is based on a triple tensor set of multipliers that are applied in a particular way to the matrix decomposition. And I believe for 4x4 matrices, they previously had to do about 64 operations or something like that. And with this game-like setup with alpha tensor, they were able to find a new matrix multiplication algorithm that only needed 47 multiplications, and I believe 49 multiplications with the last two steps. But in essence, what I am trying to do is to re-implement this matrix multiplication algorithm in Fortran and add it as an optional subroutine to LAPACK. So LAPACK currently has a matrix multiplication algorithm called dgem, but the one that I'm implementing here in the variants subfolder. And as you can see, there's been a lot of development here, but I'm calling it dgem alpha. So this is all Fortran code that the model has written itself, and it includes all 48 of the processes. I am now in the process of trying to figure out the best way to convert the math into Fortran 77 friendly code. But I have been able to derive some results where for 4 different matrix type, symmetric, asymmetric, and 2 other matrix type tests that I've run, I've gotten pretty close results. They're not within the threshold, only 2 out of the 4 of them actually pass, but I believe that I am on track to find the right kind of math to do this. So yeah, this has been integrated and is compiling and is linked to the main LAPACK repository. I just need to get the math right, and then folks will be able to use the alpha tensor matrix multiplication algorithm in the LAPACK codebase. I'm also writing comprehensive tests for comparison between the alpha tensor algorithm that I've created and the dgem algorithm. I've looked for many different ways to create this algorithm, from the Python version of the algorithm, which is publicly available. So for those of you that are used to me showing you lots of visuals, this is not quite as visual, but I believe it's a lot more technically impressive because it does prove that AI models can write Fortran and functional Fortran, and now it's just a matter of me figuring out the math so that I can create this alpha tensor matrix multiplication feature. I really hope to be able to do this by Friday. I am making great progress. I just need to get my math hat on and try harder. But thank you, folks. It was great introducing you to LAPACK and my current progress, and I will talk to you again soon.